Hello, this is Math 60, and today we're going to focus on Lesson 10. I want to recap some of the basic ideas from before. Say that we have two vector spaces. Which we'll denote by V and W. And say that we have two bases. We'll call them beta and gamma. Also, let's say that we have a linear transformation. Which I will write as T going from V to W. Now before, we introduced a couple of maps. Let's consider this map, which I will denote as phi sub beta. And remember that this takes, let's say, a linear combination and it sends that to the vector that I get by just looking at these scalars, a1 through an. So we said before that this is an example of a linear transformation. In fact, we actually gave this a name. This here is called the standard representation of V. Really, to be precise, the standard representation of V with respect to beta. So that was the first of our two statements. Second, once we fix such a linear transformation, then there is an M by N matrix called the matrix representation of T. Which satisfies the following. So that is, if I take phi gamma composed with T, this is A composed with phi beta. Now, another way to write this is by using a so-called commutative diagram. So here at the top, we'll put in our vector spaces V and W, and we realize that we have a linear transformation that goes from one to the other. Down below, we have our standard collection of n tuples and m tuples And we can map to these by using these standard representations. Now, the matrix A is what's here at the bottom. And of course, we really have to talk a bit more as to what's the idea of matrix multiplication. Again, by commutes, what I actually mean is exactly this here. The idea of commutes is I need to decide how do I go from the V at the upper left-hand corner to this FM at the lower right-hand corner. One way I can do this is by following the arrow in this way. That's what's over here on the left-hand side. The other one is I can follow the arrow here in this way, and that's what's over here on the right-hand side. Now I want to remind you how we actually find this matrix. The simple idea is that I need to express the image of the basis beta in terms of the basis gamma. So let's consider this T beta and express this in terms of this basis gamma. So what I mean by this is, let's take the first vector, v1, and let's write that as this linear combination. And of course, we can keep going all the way down through Vn, and somehow the image here we can also write as this linear combination. And once we have all of these coefficients aij's, then this is the ij entry of the matrix A. So simply put, what I'm calling this matrix A, which I can write in this fancy notation here, is simply this n by n matrix. Now I should point out that the notation here is a little bit weird. This entry here, according to V1, actually becomes this entry here that's in the lower left-hand corner. It's just a matter of how the notation works. So what I'd like to do is present some examples here. Let's start with a very simple example, and then we'll try to move up to a slightly more complicated one. Let's say for the moment that V and W are both R2, and gamma and beta will be the standard bases. So just to remind you, E1 is this vector 1, 0, and E2 is this vector 0, 1. Now, of course, if I'm given a 2 by 2 matrix A, I can figure out what a linear transformation is. So here we'll define our linear transformation as quite literally multiplication by A. So by matrix multiplication, I simply mean take this row times this column, and then the bottom row also by the same column. So if you will, we'll simply define the transformation as follows. Now my claim is that if I were to compute this matrix representation, then I'll simply get back the matrix that I started with. Now, to work out this matrix, I simply need to follow this idea from above. I need to ask, how do I go from one basis to another basis? So to this end, let's observe that I have two vectors, in this case E1 and E2. So I need to figure out what are the images of those two vectors. For E1, I'll simply multiply by this vector 1, 0. And when I do this, I'm left with this vector, A1, 1, A2, 1. Right, again, it's this times 1, 0, this times 1, 0. So this, of course, is just the first column. Now what I want to do is express this in terms of the basis gamma. In this case, of course, it's the same basis. So we'll write this out here as A1, 1 times 1, 0 plus A2, 1 times 0, 1. Right? Again, just trying to express it in terms of the basis I started with. Let's do the same thing here with E2. I want to multiply out these matrices. And now I should get back the second column. And once I do this here, let's expand it out in terms of the basis. So this is A1, 2, 1, 0 plus A2, 2, 0, 1. So again, just trying to express everything in terms of the basis I started with. Now remember what I mentioned before. This entry here should go into the lower left-hand corner. So putting these two together, then we see that the matrix we care about, well, A1, 1 still goes up here at the top. This here now goes down below. Right, so remember what I said over here, but I have to be very careful that the entry goes below. A1, 2 goes up above. A2, 2 still stays on the diagonal. And of course, that was the matrix A that we started with. So again, the whole concept here is to express the image of the basis in terms of the new basis, figure out the linear combinations, and have to be very careful that the coefficients here go in the right place. So think of this as everything here on this first row becomes here in the first column. So again, everything here in the first row, A1, 1, A2, 1, goes here into the first column. Now let's do a second example that's a bit more interesting. Now, let's let V and W both be the same. And I want this to be the collection of homogeneous polynomials in two variables. So what I mean by this is here I want functions, just like from calculus. They're functions of two variables, but they'll give me back a real number because it's a function. And I want my function f of xy to be in this form c1x plus c2y for some scalars c1, c2. So again, my functions are always in this form, c1x plus c2y. For some scalars, c1 and c2. So as it turns out, this is a vector space over R. And it has a basis. I'll call this here beta. And this will consist of V1 and V2 in terms of the following polynomials. U1 of x and y is just the polynomial x, and V1 and V2 of x and y will be the polynomial that's just y. Right, so in other words, this here is a very strange example of a vector space over the real numbers. It's a two-dimensional space. Here are the basis elements. In this case, they're not vectors, they're functions. So they're both functions of two variables, x and y, and this is exactly what they look like. Now, let's consider linear transformations from one space to the other. So just like before, let's fix a 2 by 2 matrix, and let's call this here A. And now let's maybe write these in terms of lowercase letters, A, B, C, D. Now let me be very careful to explain what is the linear transformation in this case. The linear transformation that I'll define says if I take a polynomial f, remember it's in this form here, c1x plus c2y, this should be some new polynomial in x and y. And I will get this by whenever I see x, I'll replace that by ax plus by. And whenever I see y, I'll replace that by cx plus dy. Sorry, I need to actually move these around just a little bit. This is a c, and this is a b. So again, the old polynomial was f of xy. Now, whenever I see an x, I replace that by ax plus cy. Whenever I see a y, I'll replace that by bx plus dy. So yes, I want to be very careful as to swapping the order of b and c here. Now remember how we defined f. This is some c1 x plus c2 y So now let's try to combine everything so it looks like what we had before. So I want it as C1x plus C2y. So when we do that, here I'll combine all of the x terms. So here I have an AC1 plus a BC2 times x. Again, AC1 plus a BC2 times x. Plus, now let's do the y terms. So here I have a CC1 plus a DC2 times y. Right? So now this is my new polynomial in two variables. Now you can actually check that in this case here, with respect to this basis, that this matrix representation is the matrix that we started with. So let me see if I can explain why this here is true. Well, just like before, what we have to do is take the basis elements, v1 and v2, see how t operates on them, and then figure out a linear combination in terms of the basis again. So we'll do that like this. Let's take a look at t of v1. So for v1, remember, I just had an x-coordinate. Right? For v1, I just had the x-coordinate. So I'll express that here as an AC1 AX plus CY right, because again, I only care about the x-coordinate here. And now I can write that in terms of this basis. So this will be an AV1 plus a CV2. Right, again, this here is just the x-coordinate of this. And I want to write it as a linear combination of my two functions, v1 and v2. Let's do this similarly with v2. So now I just care about the y-coordinate. So here this is bx plus dy. And we'll write this in terms of v1 and v2. Now remember what I said before. The first number here is always in this entry, but this number here is always the lower left. This number here is now the upper right, and this number here now is the lower right. So just by looking at these four coefficients, I see I get back to matrix A again. Now, from here, there's fortunately a lot we can do with matrices. So we want to see how that's related to an operation on these linear transformations. So for the moment, let me talk about composition. Let's say that we have three different vector spaces. Let's say that perhaps V, W, and U are vector spaces over a field F. And what I want to do is now consider a couple of different linear transformations. So let's say that perhaps we have a linear transformation T, going from V to W. Sorry, this here should be a Z. Sorry. V, W, and Z are my vector spaces. And let's say I have another linear transformation. In this case, I want to call this U, going from W to Z. As a picture, what's happening is this. So here I have V, here I have W, here I have Z. T maps from V to W, and U maps from W to Z. And what I'd like to know is, what can I say about the composition of these? So by the composition, I'll denote this as U composed T. So this goes from V to Z. Right. In terms of a picture over here, I simply am just going from left to right. And again, this is what I'm denoting as U composed T. Even though I'm going from left to right, I always write the symbols from right to left. So what becomes first is over here T, and then what becomes last is over here U. So yes, it is backwards, but that's the standard notation. So there are three main statements that I'd like to make here. In the notes, this will be theorems 2.7, 2.9, and 2.11. So now let's try to be a bit more precise here. Let's say that we have V in terms of circles, W in terms of the boxes, and let's say here Z, which I'm not going to put anything around. Say that these are vector spaces defined over a common field F. And of course, for all practical purposes, F is just the real numbers, although it doesn't really matter. So my three statements are as follows. Number one, let's denote the script L VW as the collection of all linear transformations T going from V to W. Then I claim that this is a vector space. In fact, it's a vector space over F. So of course I have to explain what are the operations of addition and multiplication. But we'll come back to that in just a moment. Number two, say that we have two different transformations, as what I've written over here on the right. So again, let's say that T and U are linear transformations. then the statement is I can look at the composition. This was this U circle T going from V to Z. So the statement is that this is also a linear transformation. Right. And for the third one, we're going to combine what we said earlier about this weird matrix here, this matrix representation from B to gamma. So let's say that V, W, and Z have bases. Let's call them beta, gamma, and alpha. Right, so beta is the basis for V, gamma is the basis for W, alpha is the basis for Z. Then, as a product of matrices, we have here the matrix representation of this composition is equal to the following product of matrices. So now let me say some words behind what all of these are saying, and then we'll try to come back and sketch a proof. So here's some remarks. So first remark, let me just quickly tell you what's the definition for the operation here on this LVW. So again, LVW is the collection of linear transformations from V to W. So first, I can define the vector addition as follows. Given two linear transformations, then let me define their sum as that linear transformation that sends V to this sum here. So again, if I have a vector V in our vector space capital V, I can look at this vector T1 of V that's in W and this vector T2 of V that's in W. So if I look at this definition, this says this is that linear transformation that sends V to the sum of elements in W. So that's why typically we like to write the square box as the operation on this script L. Similarly, for scalar multiplication, if we're given, let's say, a scalar C and perhaps a linear transformation T, then let's define this scalar multiple as that linear transformation that takes V to this scalar multiple. So again, given a vector V inside of capital V, I know what T of V is, that's some vector in W, and I can consider the scalar multiple of that as another vector in W. So when I write C times T, I really mean that linear transformation that takes v to the scalar multiple. So again, I have a square box that's an operation on linear transformations, and then I have another square dot that's an operation also for this linear transformation. So we'll try to see examples of this later. Next, let me try to stay a little bit behind what's happening here with statement 3. Now, there is a picture that explains what's happening here. So what we'll do here is let's write v, w, and z here at the top. So remember that the operations here are t is a linear transformation from v to w, and u is a linear transformation from w to z. Now we also have our standard representations. Let's perhaps write them this way. So this will be some phi beta, this will be some phi gamma, this will be some phi alpha. Right, again, this will be what happens when I look at the linear combinations and just stare at the coefficients. And here at the bottom, we'll have our matrix representations of t. Notice that here I'm going from beta to gamma. And here I'll have my matrix representation for u going from gamma to alpha. And somehow here at the top, I'm looking at this composition, u compose t. Again, remember that it's always read in the opposite direction. Whereas here on the bottom, I can do the same thing. I can look at this matrix representation that's now going from beta to alpha, right? Because I'm starting at beta, ending at alpha. And much in the same way that I can think of u compose t as first I do t, then I do u, there's a similar corresponding idea here with the matrices. So somehow I can multiply matrices. So later, I'll say exactly what do I mean by that. But the main idea here is that this just comes down to a numerical computation. I'm just going to multiply things out, and then I know exactly what's happening with the transformation. So I don't have to worry about a very abstract construction. I can write everything very concretely here just by multiplying things out. Okay, I'm going to leave the proof of the first one as an exercise because that's just a matter of working through the 8 different axioms of what it means to be a vector space. Instead, I want to focus on the latter 2. So let's spend some time here discussing why is the composition of 2 linear transformations, once again, a linear transformation. So here I just want to do a sketch of the proof. So let's start by showing 2. That is to show that the composition is a linear transformation. I really have to show 2 things. So first, I have to show that this preserves addition. So if I have 2 vectors, x and y, then let's consider now the sum of these. Now I have to be a little bit careful. These are elements in Z, so I need to have the operation in Z. Right? In this case, it's the plus with no circle, no square. Similarly, I need to see what happens with scalar multiplication. So here I should have a scalar multiple of the image. And again, this is scalar multiplication in Z, so no circle, no dot. Right? So I need to show that the composition preserves addition and the composition preserves scalar multiplication. So to this end, let's pick C and F and X and Y in V. So let's try to do the very first one here. So if I want to consider U compose T of X plus Y, let's first figure out what's the definition of this. So remember, first I look at the image under T, and then I look at the image under U. So really the definition of this says, first let's consider what happens under T, and then I need to look at what happens under U. Right, so this here is some element of V, and now I apply U, and then this is some element of W, and I apply this, and that's some element of Z. So this is by definition. Right, again, that's the definition of what composition is. Now, I can break it up because this here is true because T preserves addition. But now here I have the sum of two elements in W. So I'm going to write this image as the sum of two elements in Z. And of course, this is because U preserves addition. Right? So again, now I have the sum of two elements in Z. And now let's just work backwards to what was the definition of composition. And again, this is by the definition of what composition is. Now let's also do part B. It'll be very, very similar. So here I want the composition, and here's the scalar multiple. So of course, first, operate on the scalar multiple, and then I see what is the image under U. So this is by the definition of composition. Now from here, I can pull the scalar C out front. And of course, this is the scalar multiple in W. And this is because T preserves scalar multiplication. But now here I have a scalar times an element of W, so I can bring that out front once more. And again, this is because U preserves scalar multiplication. And finally, if I just wind back through to remember what's the definition here, this is simply the composition of these functions. So again, this here is by the definition of composition. Okay. So finally, I want to show statement 3. So what's actually happening here with the product of matrices? And working this out, I actually want to explain what is the definition of the product of two matrices. Now for this here, we just have to do a discussion as to what are the various coefficients. So let's fix our notation here to make sure we're all on the same page. So explicitly denote the bases. So beta we'll write here in terms of V1 through Vn, and this is for V. Gamma we'll write here in terms of W1 through Wm for capital W. And then finally, alpha we'll write here as Z1 through Zk for capital Z. Right. And the notes actually have this as P, but I realized that I screwed up the notation over there, so I won't make it more confusing. So again, here I'm just going to fix my bases for V, W, and Z. Now remember, the way that we work out these matrices here is we have to see how do we express the new bases in terms of the old bases. So it's a matter of just staring very carefully at all the coefficients and matching everything up. And that's what we're going to do. So first things first, let's try to compute what are these two matrices over here, matrix representation for T, matrix representation for U. So to find this matrix representation for T, remember how we're going to write this. We have here T of V1 as this linear combination. Right, so this A11 through AM1, and we'll keep going down the list through TVN. So this is A1N, all the way down through AMN. And remember now that Aij is the Ij entry of this matrix, this T beta gamma. Right, that's the definition. So if you will, what's happening here is that in this first row, these entries become the entries in the first column, and then these here become the entries in the last column. Now we could do the same thing here for U. So to find this U gamma alpha, then let's ask what happens when I apply U to each of these W's. So this is some maybe B11 times E1 through perhaps, let's say, some BK1 times ZK, all the way down through WM. And now this will be some B1M times Z1. And this will be some BKM times ZK. And just like before, this entry Bij is the Ij entry of this matrix representation U gamma alpha. Right. So I have the A's that correspond to this matrix T, or I should say this matrix corresponding to T, and have the B's corresponding to the matrix for U. Now what we need to do is look at the composition, but do it two different ways. Now, on the one hand, what we can say is, to find, let's say, the matrix representation for the composition, then let's just write everything out going from the basis beta to alpha. So we'll just pick elements in the basis for beta. And these will be some coefficients. Let's say here maybe C11 through perhaps, let's say here, CK1 all the way down through Vn. So this is C1n. And CKN. So just like before, Cij is the ij entry of this matrix representation for the composition. So again, I have A's, I have B's, I have C's. Now, what we're going to do here is observe there is a second way I can get the C's. What I could do is I can take a look at what's over here on the left in terms of the T's, and let's apply U to everything. So again, I will take my T of, let's say here, VI, and let's just apply U to everything. So I'll take all of my T's up there and just apply U. So when we do this, and again, I'm not going to do this more because it just gets very disgusting here on the board, I'll find the following formula. So Cij is actually equal to this sum here. So here I have a BIP times APJ. So again, if I just simply take what's on the left, if I apply U to that, then you see that U is a linear transformation. So really what I'm going to do is I'm applying U to all of these W's here. But whenever I see a U and a W here, I'm going to substitute in these over here. So again, I'll have each one of the W's here. I'm going to substitute that in terms of the B's. And just when you stare at everything and multiply it all out, you find this expression here. So this actually gives us a definition. Let's say that maybe Aij is the ij entry of a matrix here, A. And let's say perhaps Bij is the ij entry of a matrix B. then let me define this product, which in this case will be B times A. This will be that matrix with ij entry. So here Cij will be this here. So here I have a sum, P goes from 1 to M, BIP, APJ. Now I should perhaps be a bit more precise here, so let me be a little bit careful. A is actually an M by N matrix, because it goes from V, which has dimension n, to W, which has dimension m. Again, it goes from V to W. V has dimension n, W has dimension m. B, on the other hand, is actually a K by M matrix. And this is because W has dimension m, Z has dimension k, right? So K by M. So this matrix C, I have to be very careful here, goes from V to Z. So this is actually a K by M matrix. And here are what the entries are. So I'm actually defining matrix product for you. Right? We'll come back and we'll see examples of this later. So with this definition, where of course I want A to be this matrix representation of T, I want B to be this matrix representation of U. Let's see here. Then this means that this C should be the matrix representation for the composite, which of course now is just the product of these matrices. So the main thing I want you to take away here is I'm defining the product of matrices such that composition makes sense. So again, if you're wondering why do I have this weird definition here, I'm making this definition so that the composition makes sense. And again, we'll see lots more of examples of this. Right? Okay, let's call it a day here then. So everyone, please have a good weekend and see you on Monday.